All right. Welcome everybody to this week's GOCC. Today we're very happy to have Antwon Park telling us about Smith's normal form of graphical Hermite simplices. Before we begin, I'd like to just remind everybody of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that being said, Antwon, take it away.
Hey, thank you so much. Just quick warning, I'm feeling a little bit sick, so I apologize if there's any coughing or any unpleasant sick sounds that come out of my mouth. But I'll be talking to you all about Smith normal forms and graphical Hermite simplices. And so a basic outline for what this talk is going to look like. We're going to start by talking about what are these graphical Hermite simplices, moving on to what is Smith normal form and kind of how to be thinking about them. And the rest of the talk is going to be a lot of proof by examples. I'll be sharing some of the things we were able to find. So lots of examples. Please feel free to stop me if there's any questions about things. But yeah, let's get started with DAGs. So an acyclic directed graph. Um, the acronym doesn't go quite the right way because a directed acyclic graph and an acyclic directed graph are technically different things, but we call them DAGs. It's a simple directed graph on n vertices where the labels uh, are from 1 through n, and each edge has an orientation, and no directed cycles exist in G. So here I have two examples of these acyclic directed graphs, and no matter how you walk on these vertices, you have to step in the direction of the arrows, and there's no way to end up back where you started. One thing that you can do to help ensure that you always have this orientation is you can order the vertices such that they always point to a larger vertex. So here, both G and G prime have this property where every edge starts at the lower vertex and points up to a higher one. And so another thing that we need to talk about is Hermite. So a matrix A is said to be in Hermite normal form if A has only non-negative entries, if A is upper triangular, and if each column of A has a unique maximal element located on the main diagonal. Here I have two examples of matrices in Hermite normal form. The way that I like to think about Hermite normal form is you focus on that diagonal. So on the left, I have a 2, 5, 3, 11 on that main diagonal, and everything above those diagonal elements have to be smaller than those particular entries. On the right, the diagonal is all 2s, and everything above it is either a 0 or a 1. In general, we're going to be working with Hermite normal forms kind of this flavor where everything above that main diagonal is a 0 or a 1. And this is going to give us what graphical Hermite simplices are. Uh, Take a diagonal vector. We're, for now, we're just going to say that your diagonal vector has to at least be 2. Things work well if you have it be 1, but kind of to keep things interesting, you kind of need to have things at least bigger than 2. And if you have a DAG with the topological ordering, that's where you have the vertices are, the edges are oriented pointing from smaller vertex to higher vertex. You're going to get a graphical Hermite simplex. So I'm not going to define it per se, but I think going through a few examples, it'll be clear how to define these graphical Hermite simplices. And so here's the first example of it. We have seen these graphs of these matrices before. And so uh, to kind of keep it with the notation, instead of saying A, I'm going to denote it as A subscript. My diagonal vector is 2, 5, 3, 11, and it uses information from the graph G on the left in order to produce what the matrix looks like. So again, it's clear that the diagonal is 2, 5, 3, 11, but how am I assigning the ones and zeros? It's by the edges. So here I have that edge between 1 and 2. That's going to correspond to a 1 appearing in row 1, column 2. If I do it again and then on another edge, I have an edge between 1 and 3. So that means that in row 1, column 3, there should be a 1 there. The last edge in the graph is between 2 and 4. So on the second row, the fourth column, I have a 1 there. There are no other edges in the graph, and so everything else in the upper triangular portion is going to be a 0 for me. And so, kind of with a more complicated example, here we had the G prime and A prime from earlier. Again, the notation is going to be, it is going to be vec2 as my vector, and G prime is the graph that I'm using. Quick note, we're going to be looking at the case where you're working with a constant vector, and we're going to just have the little, if you have the little vector arrow on top of your number, that's just saying, hey, it's going to be that constant vector all the way down from the top left down to the bottom right. But if we go through each edge, I have an edge between 1 and 3. So there is a 1 in row 1, column 3. Same thing if I have the edge between 1 and 4. I have a 1 in row 1, column 4. And if I do the same thing for each edge, row 2, column 4, row 2, column 5, row 3, column 4, and so on for each of these edges, that is where I'm adding in those ones. There are 7 edges in G prime, and so I have 7 ones appearing in my graphical Hermite simplex. So, questions so far are kind of about like how we're defining these things. Okay. And so the idea behind these graphical Hermite simplices is that there has been a lot of simplices in the literature where if you look at kind of a way to represent them using a matrix, their matrix is in Hermite normal form. And so these are just trying to uh, generalize those kinds of matrices, and we're trying to see if there is a way that the combinatorics of the graph can inform us about algebraic properties of the matrix or geometric properties about the simplex. And so this is why we've been thinking about the simplices, and we have some results pertaining specifically to the Smith normal form of these matrices. So uh, let's start out by talking about what Smith normal form is. Um, so if you have a matrix A, there is a way to multiply A on the left and right by unimodular matrices. Unimodular means that their determinant is 1 or -1. It's like area preserving. But when you do this transformation, you're going to end up getting that a diagonal vector is going to form where the alpha i's along the diagonal divide the following term. So alpha I divides alpha I plus 1. This is called the Smith normal form. The alphas are called the elementary divisors of A. Equivalently, they're also called the invariant factors of A. These two are interchangeable. And if you do a lot of like finite abelian group stuff, you might recognize this. This is computing. When you compute the Smith normal form, it's equivalent to computing what is like the product of finite abelian groups if you're given what the matrix is. But I think we'll just stick with a lot of examples because we're more so focused on the elementary divisors, not just on so much what is the overall Smith normal form. So here we had the two examples from earlier. Uh, on the top one, if you go through and figure out what the transformation is, or just give it to a computer in order to solve, you're going to get that your diagonal matrix is going to be 1, 1, 1, 330. So kind of everything collapses into that last spot in my diagonal matrix. And on the other one over here, similar thing, give it to a computer to solve and ask for its Smith normal form. You're going to end up getting that this is its Smith normal form. We're not going to focus on how you are getting these necessarily. Smith normal forms are notoriously very difficult to compute in general, but if you have particular matrices, it is not too bad to do. One thing to note is that kind of the number of non-one factors you're seeing has there's things that the number of invariant factors that you're seeing that are not one kind of tell you something about the structure of the matrix or the corresponding group it's representing or something. So whenever you have this case where you have a single non-unit elementary divisor like that 330, we say that the matrix has a cyclic cokernel. And so one of the first things that we were thinking about is when do matrices of these graphical Hermite simplices have cyclic cokernels? And in order to do this, we're going to have to think about how are we going to compute what these elementary divisors are. When you're computing elementary divisors, you can do so using this formula. If you have the I by I minors, that are the determinants of the I by I submatrices, if you compute all the I by I minors, find their GCD, that's going to be this delta sub I. And dividing delta sub I by delta sub I minus 1 is going to give you what alpha I is. And so, as an example of working with this, here is this kind of small-ish 4 by 4 example we've been staring at for these last several slides. I'm going to share with you kind of a quick proof to show that delta 3 is going to be equal to 1. If you can show that delta 3 is equal to 1, what you're going to get is that kind of delta 1 and 2 are also forced to be 1. And that's going to force that delta 4 is going to have to be the product of the diagonal, in this case 330. And you get essentially from this delta 3 being 1 that you are going to have a cyclic cokernel here. And so this is like the flavor of stuff that happens when you're working with Smith's normal form and you're interested in these elementary divisors. You really are trying to figure out like submatrices and figuring out like what is a clever way of getting the determinants to like match up in a really nice way. And so uh, if I look at this A matrix, one thing that I can do is I can say, well, I'm trying to find 3 by 3 submatrices with kind of nice determinants. So one thing that I'm going to do is I'm going to take the submatrix where I remove the fourth row and the fourth column. That's going to leave me with this submatrix. I'm also going to do the same thing where I remove the third row and the third column, and then the second row and second column, and then the first row and the first column. And so all these four 3 by 3 submatrices are upper triangular. And so computing their determinant is actually very easy. On the first one, we're going to get that the determinant is 30. The next one is going to be 110. The next one is going to be 66. And the last one is going to be 165. And so I have these four determinants, um, and their GCD alone is going to give me 1. And so even if I try to find all the other 3 by 3 submatrices, because I found 4 that are as a set coprime, that tells me that the delta 3 has to be 1 here. And again, that tells me that the Smith normal form for this matrix has to be 1, 1, 1, and then everything else in that last invariant factor. And so this is the kind of the flavor of stuff of things that you're interested in if you ever want to talk about Smith normal form. Either you have to find some ways of translating into algebra, or if you want to kind of stay in matrices, you have to figure out how to work with the minors. So uh, another example where you see these cyclic cokernels popping up is when you have a path graph. A path graph is what you think it would be. P sub n is defined to be just the numbers 1 through n, where each adjacent pair of numbers have an edge corresponding between them. So here we have P4. There is an edge between 1 and 2. There is an edge between 2 and 3, and an edge between 3 and 4. And this time, I don't know what my diagonal is, but it doesn't matter. I can always find this 3 by 3 submatrix. If I remove the first column and the last row, that's going to push all of those ones in that off diagonal down to be onto my main diagonal when I'm considering that submatrix. So this gives me that delta 3 is equal to 1. And so kind of by a very similar, like by the identical argument from the previous example, you're going to show that this matrix also has a cyclic cokernel. And so both of these examples generalize. We did it for relatively small sizes just so that the examples were a little bit clearer. But for any size matrix, what you're going to find is that if the entries of your diagonal vector are pairwise coprime, doesn't matter what your graph is, you're always going to end up with a cyclic cokernel. If your graph is a path, doesn't matter how long it is, and it doesn't matter what D is in particular, you're always going to have the cyclic cokernel. And you might see in the third case, we have this G contains a path of length n, and D is this constant vector m. If you have this case, you're also going to get a cyclic cokernel. This case is actually really interesting because when you restrict yourself to the case where D is this constant vector, whatever your graph is actually tells you a lot about what the Smith normal form is going to look like. And so the rest of the talk is going to be a proof by example of essentially this theorem. This theorem will come as a corollary of some like key lemmas that we'll talk about in a little bit. But from here on, it's going to be a lot of examples, a lot of like data, a lot of trying to spot patterns and things. So before I move on, though, are there any questions from the people in the audience?
I had a quick question. So when you're saying at the beginning that you were calling these like simplices, is am I
Yeah.
thinking of it as like I'm just taking like the convex hull of the columns or something like that? Or
Yeah, so we're thinking of this as an n by n matrix. So those are kind of
Mhm.
corresponding to end points in Rn. The last point you need to form the simplex is take the origin. So take the 0, 0, 0,
Gotcha.
0,
Okay.
1. Um,
Perfect. Thank you.
yeah, because again, for a lot of simplices kind of use that as a point, but it doesn't impact like the number theoretics in particular. So you kind of just can cut it off. And so then you're left with this nice square matrix that you can study. And also, you should be thinking of these with like a one in the top coordinate. You're thinking of like the cone over the polytope, but again, it makes it that like all those ones don't impact the number theory parts of it very much. So we're just restricting ourselves to the case of just looking at the n by n and not the cone over that polytope. But yeah, okay. So from here, I am just going to show you we have this kind of G prime, which is like sufficiently complicated enough to like illustrate some nice things, but it also will show something that I think is really cool. So if I'm thinking about kind of properties of graphs that can inform me about things, let's think about what is the longest path that I see here. I see that there's a path between 1, 3, 4, and 5 that happens to have four vertices on it. So is it a coincidence that the largest invariant factor that I'm seeing is 2 to the fourth? If I do this for a bunch of other random graphs, you kind of see a similar pattern. You can change 2 to be a 3 or a 4 or a 6 or whatever constant you want. You're always going to end up seeing that the kind of number of vertices along a path tell you something about what that largest elementary divisor is going to be. So to kind of talk about it, um, a path is a sequence of vertices where each of the adjacent vertices have an edge between them. Uh, One place where we're going to differ is what is the length of a path. Normally, the length of a path is the number of edges that you're using. But because of kind of what you saw, where you want to think about the vertices you're hitting, we're going to say that the length of the path is the number of vertices that you hit. So there's like an off by one thing that if especially if you're really used to thinking about the normal length of path, there's an off by one you'll have to deal with, but it's not too bad. And I think the examples will help illustrate kind of why we want it to be this way. So here I have a family of graphs that I'm calling B sub I. Uh, the way you are building B sub I is you take one on the left, you take your last vertex on the very right, and you're going to place I mini vertices in between them and connect one to each of those intermediate vertices, and then connect that last vertex to all those intermediate vertices. So the way to think about this is that these are graphs with maximum length 3, and it has I mini paths of length 3. So I'm gonna share with you the so take the Smith normal form, throw away all the ones. What you're gonna get is that if you use 6 on that main diagonal, these are those elementary divisors you're seeing. 6 cubed is 216. So I'm not seeing 216. So I may have just lied to you all. I'm not seeing 6 cubed showing up. But again, coincidences here. 216 divided by 2 is 108. I happen to see that in B2. 216 divided by 3 is 72. I'm seeing that in B3. And if we zoom out and look at kind of more data, you see that this is the pattern that shows up. 216 does show up on some of these elementary divisors, but I'm also getting 108, 72, and even a 36. And that is respectively dividing by 2, dividing by 3, and dividing by 6. And I think this is also really fun. The places where you get 216 are exactly where I is co-prime with 6. So there's something here about kind of co-primeness with 6 that is actually giving me 6 cubed. And the kind of theorem that we were able to prove regarding these elementary divisors is that if you have a DAG G and you let H be the length of the longest path in G, the largest elementary divisor is bounded by m to the h. And you're going to hit that if you ever have a pair of vertices where the number of paths in G of length h from U to V is co-prime with M. So when you have these co-prime number of paths of maximum length, that is going to give you uh, the case where you have exactly M to the H showing up as that largest elementary divisor. And so uh, the goal for the rest of the talk is to kind of be thinking about this and kind of, again, proof by a lot of examples. And hopefully you can kind of at least see the pattern. And we'll talk a bit as to why this is the case. And I think it's actually a very beautiful argument as to why these theorems are true. Before I move on, how are we feeling about things? Are there any questions people have about anything from this section? Okay. So, uh, the next thing is kind of talking earlier when I was talking about Smith normal form, you want to be thinking about the minors. And so here I have G prime, here I have the corresponding simplex, and I need to try to find like determinants that give me what I want. And this is, at least for this example, this is the submatrix I want to pull out. So if I take this 4 by 4 submatrix, the way I'm going to build it is by thinking about what is my longest path. My longest path is from 1 to 5. So I'm going to start at 1 and then move 4 numbers over to get to 5. So I'm calling this submatrix M sub 1 comma 4. 1 is where I am starting at, and I need to go 4 numbers out to hit the end vertex that I'm trying to get to. And uh, the way you're going to kind of take this submatrix is you're going to remove column 1 and remove row 5 and take the submatrix that kind of fits into that corner. Anyways, once you have this particular submatrix, uh, you can compute its determinant in a pretty fun way. So one thing that I'm going to do is to help make it a little bit cleaner, I'm going to get rid of that matrix. I'm only going to focus on this minor. And I am going to compute the determinant by looking at all of the paths from 1 to 5. So the first path that I have is that 1, 3, 4, 5, that longest path. And I missed out on hitting 2. So because I missed out on a single vertex, that's going to give me a -2 in part of my sum. The next path that I could do is instead of hitting 3, I can skip over it with a detour and do the path 1, 4, 5. And now I've missed out on both 2 and 3, so that's going to correspond to a -2 squared. These two paths are the only two that go from 1 to 5, so my final determinant is just 2. So somehow, if I want to compute this particular minor, I just need to count the paths and count the numbers in between that I'm missing out on. So to kind of give a more concrete definition as to what that submatrix is, uh, M sub A comma B is going to be the B by B submatrix of our graphical Hermite simplex for some constant vector M. And you're going to take the rows A through A plus B minus 1 and the columns A plus 1 through A plus B. Um, it's a little bit weird as to why it has to be kind of these corresponding rows and columns, but the intuition you should have about these submatrices is that they're encoding all possible paths from A to A plus B. And that is why the determinant is going to end up being the sum over all the paths. And so let's do some more examples. Here we're returning back to that like branching graph. Here I have B3. I have what the corresponding simplex is if I use 6 as that main diagonal. And taking the m sub 1 comma 4, again, I'm starting at 1 and I'm ending at 5. So I need to go 4 away. I'm taking this 4 by 4 submatrix. That's like the top right corner of my matrix. And then I'm just going to count the paths, really. So get rid of what the simplex used to be, so just so we can focus on what the graph is. What I'm going to get is if I go along the top, the 1, 2, 5 path, I am missing out on 3 and 4. So that gives me a negative 6 squared in my determinant. If I go through the middle, I miss out on 2 and 4. So I also see a negative 6 squared. And I can go along the bottom path, 1, 4, 5, and that's going to correspond to negative 6 squared again. And so what I'm going to see is that the determinant of this um, submatrix is 3 times 6 squared. And if you remember from the data I was showing earlier about these graphs, the largest elementary divisor for B3 was off by a factor of 3, and that 3 is coming up in this particular minor. So that is why you're getting this off by 3. It's the number of paths of length 3 inside of here. So
Just a small question.
yeah,
So, when you're computing the path, could you go back to like one of the colored things? So, okay, I just want to understand. So the yellow on the top is 1 comma 4, and that's why it's 1 to 4. And the colored yellow on the bottom is 4 to 5.
yeah, if you
Is that correct?
highlighted those in the big simplex, those that correspond the edges between 1 and 4 and 4 and 5. So you are correct.
Right. And the red
When you like,
ones,
yeah.
uh, yeah, and the red ones are
Yeah,
1 and
so the way to think about this,
mhm,
there is a definition for the determinant that is based on permutations and kind of the
mhm,
sign of the permutation. Um,
mhm,
what you're essentially doing is you're finding like permutation, you're essentially finding spots in the matrix where you're kind of highlighting one element in each row and one element in each column. And so, kind of when you're missing out on particular vertices, what that's going to correspond to is that you are able to grab that like 6 or the M that's along that main diagonal. So that's why those sixes are being highlighted. If I use the path 1, 4, 5, that's going to give me that I'm having this like these two sixes, the first one corresponding to the vertex 2, the second one corresponding to vertex 3, and those are making their way into these like negative 6 squareds. And those are negatives because if you're thinking of cofactor expansion, they're off the main diagonal by 1, so they have this negative sign associated to them.
mhm.
So,
Okay.
yeah, that is also why they're highlighted in this way, so that if those of you who are, excuse me, for those of you who are comfortable with this like permutation definition of what a determinant is, what we are essentially doing is translating that permutation sum into a sum over paths. And it is like a
Right.
just like a proper like it is really the same thing, and it's just a different perspective on it.
Got it. Yeah, that makes
Yeah.
more sense. Thank you.
But okay. And so, yeah, so here we have this one. And one thing that I'm going to claim is that we've been looking at the submatrix. I've been showing it to you to kind of see what it looks like, but I really don't need it. So here I have a sufficiently complicated example, but I claim that regardless of what your diagonal is, the thing you see down here is going to be what the determinant is going to be. So 2 comma 7 means I'm starting at 2, ending 7 away. So I'm ending at 9. And if I go through each of the paths, each of these terms corresponds to one of the paths from 2 to 9. So this first path I have going from 2 to 9. I miss out on 6 vertices between 2 and 9. So 3, 4, 5, 6, 7, and 8 aren't showing up on this path. So I get a negative m to the 6th showing up. I can do a little bit of a zigzag where I can go 2, 3, 8, 9. So that's going to mean I'm missing out on 4 vertices total here. So that's a negative m to the 4th. And then finally, I have this long path along the top of 2, 5, 2, 3, 5, 7, 9. I am missing out on 4, 6, and 8. So I get a negative m cubed as the final term in this determinant. And so this, again, is not a coincidence. This is going to be true for all DAGs. So let G be a DAG, then the determinant of the B by B submatrix M sub A comma B of our graphical Hermite simplex is equal to the sum over all possible paths from A to A plus B. And on each of those paths, you're going to do negative m raised to the b minus length of the path plus 1. And this is just a way of saying the exponent's going to correspond to the number of vertices you are missing. And so this was like the key insight. In our paper, we have a slightly more general version of the statement, but for the example of the constant diagonal, it is just going to be this negative m raised to the number of vertices you have missed on that particular path. And so this is a great tool, and it's going to help us answer the question, what is delta of n, delta sub n minus 1? So remember that I'm trying to compute the GCD of the n minus 1 by n minus 1 minors. And with this, you can then show that uh, we have a notation here, a sub c comma r is the n minus 1 by n minus 1 submatrix of our graphical Hermite simplex obtained by removing row r in column c. So I can tell you that if you remove a particular column in a particular row, whatever that submatrix is, its determinant essentially looks like m to the n minus the length of the path. And so this is a way to compute all of the n minus 1 by n minus 1 minors. And so I can compute what delta of n minus 1 is, and that tells me what my largest elementary divisor is. One thing about this formula is that I don't care what P actually is and what vertices P goes through. I only care that my path is of a particular length. And so I can gather terms together based on the length of the path. And so here what you end up getting is that instead of iterating over the paths, you iterate over possible path lengths. So you can't have a path of length 1 because you're counting the number of vertices. So you count how many paths have length 2, starting from R and ending at C. And similar thing, if you do this for all of them, you're going to get this kind of polynomial in M, and uh, the degree of this polynomial, sorry, not degree, the smallest term you get in this polynomial is m to the L minus h, where h is at maximum path length. And so that is how you're able to conclude what is your largest elementary divisor. And you get an upper bound depending on what f sub c comma r is. But if you know it's co-prime, then you know it's going to be actually equality. And so uh, this is the general idea, but hopefully, kind of with the previous examples, you can understand where we were getting these formulas from. It was from a lot of pattern recognition and just trying to get at. Sometimes you end up getting that the largest elementary divisor is exactly m raised to h. Other times it's off by a factor. Why is it off by this factor? And it comes down to this essentially. So I think this is pretty cool. It was very fun to have figured this out and to have written about it. Um, and so to kind of finish us off, I won't be taking the full hour. I want to be talking about uh, a conjecture that we have that we kind of don't quite have we weren't able to figure it out, but we still think that this is an interesting thing to figure out. Um, so to illustrate this point, I'm going to be bringing up the examples of what we call bipartite DAGs. They are kind of what you expect based on the diagrams. Um, a bipartite DAG is a bipartite directed graph, but all of the edges go from one part to the other. So there's no kind of crossing, or there's no like edges going in the opposite direction. And so here I have two examples of bipartite DAGs. And if we care about maximum path length, by forcing it to be bipartite, we are restricting the length of these paths. In particular, bipartite DAGs have a maximum path length of 2. So, kind of by the previous result that we had, elementary divisors of these particular of yeah, elementary divisors of the graphical Hermite simplices when you use a bipartite DAG, they are bounded by m squared. And we've been working with like 6 as a m just to show that you don't need primeness at all. But here we are going to restrict that you have to be working with a prime. If you are working with a prime diagonal, one thing that you're going to get is that the elementary divisors are 1p or p squared. That is obvious from the way that you're defining the divisibility conditions on your alphas. But this is the cool part. Uh, Ignore the diagonal. Only focus on that directed adjacency matrix so that it's like the upper triangular portion of our simplex. The number of ones showing up in your Smith normal form is equal to the rank of that matrix over the finite field Z mod PZ. And because we're working in this case with bipartite DAGs, for every one that shows up, there is a corresponding p squared that shows up. So the number of p squared elementary divisors is also going to be equal to that rank. And so this is nice because this is going to give you a way to compute the Smith normal form without ever having to consider what P is. Um, so just simply based on the information of the graph, you can fully determine what your Smith normal form is. But this is the part that we have kind of left as a future direction that we can take for this Smith normal form project at least. We think this is true for all graphs. So in the previous proposition, it was only for the case where you had these bipartite DAGs where you have a maximum path length of 2. Here, if you just have an arbitrary DAG, what you're going to see is that the number of ones showing up in that Smith normal form is exactly equal to the rank of the adjacency matrix. Um, we've tried several stabs at this to try to figure it out, but when you're working with arbitrary DAGs, it gets a little bit weird to kind of find the right minors. But we have done plenty of examples and computer searches for this, and we have yet to find a counterexample to the statement. So we're pretty sure that this is true, but we don't know what right perspective to be having to seeing the right patterns. But that's all I have for you. Here's a preprint if you're interested in reading more, and thank you very much.
All right. Any questions for Antwon? Oh, I have a question. Do you know if the matrices you're getting here are totally non-negative? Like, are all the minors non-negative?
Oh, like what the determinants are?
Yeah,
The determinants could be negative.
they could be negative. Okay,
Yeah, in particular, if you grab one where you only have like a length, one path of odd length, then you're adding up a bunch of negative things.
I
I
see.
can,
Okay,
yeah, I can go back to, yeah, like this one right here. Because what you're doing is negative m raised to some powers. If all you have are odd powers, you're gonna get a negative determinant.
gotcha. Okay, because I know if you have like a totally non-negative matrix, there's some way that you can like associate a like a planar graph with like n sources and n sinks somehow. So, but if these aren't totally negative, then I think my question doesn't make sense. So, never
Yeah,
mind.
I'm pretty confident that like it is possible to construct an example where it's only odd powers showing up. So yeah. Yes.
So when you compute these, you always get a sum over some, like a linear combination of powers of m, right?
Hmm.
Uh, so on your diagonal, could you start with powers of m instead of
Yeah,
starting with a
so
constant m vector?
we had some initial results way in the beginning where you kind of had like arbitrary diagonal stuff. Um if you restrict to like powers of primes, you essentially walk away with like composite issues still. So like um
Mm-hmm.
there's nothing special about powers of primes. Uh, it really is if you're working with a constant vector or not. And
I
and
see.
and that really is kind of the key thing. Like you can construct like yeah, there's a in the paper we constructed a few examples where if you're working with like composite numbers, it's possible to like perfectly construct graphs where it's gonna mess up Smith normal form results and stuff. So
Mm-hmm.
if you want things to behave nicely, you really do need to restrict to the case where it's just a constant vector. But
I see. And in your examples, I don't know if that was true, but you do get a lot of negative m to the power something, right? But that's not necessarily true.
um, so the way it works is that because of the way I'm defining these minors, I'm always
Hmm.
pushing that like main diagonals of twos or of m's really. I'm pushing it
Hmm.
down one into the off diagonal. Um,
Right.
and so uh you you essentially are whenever you grab one of these tubes, it always comes with a negative sign attached to it. And I know that the ones might also contribute negative ones, but they also cancel out in the end.
Okay. I see.
Yeah.
Huh. Hmm.
Yeah,
Okay.
and if you go through the
Sure.
cofactor expansion, every time you grab that m, it's always gonna end up
Mm,
being this like negative two that you're grabbing. Yeah,
right.
and
Because
like
the subdiagonal is just off and even
yeah,
n plus n, so
and
n plus n plus 1.
the proof that we have for this lemma, where is it? The proof we have for this lemma uses cofactor expansion in order to get to
Hmm.
it, but a cleaner way to think about it is by thinking about that like the using permutations to define
Right.
what a determinant is. And that one is not
Hmm.
it is not as clear as to why you only get negative m's whenever you pick one up. But
Yeah.
All right. Well, thanks so much for the talk.
yeah, thank you for having
I
me.
think I'll stop the recording now.